to Stefan. Could you please?
Yes, thanks for the question. So we would say very reasonable seems to use Adam or RMS prop, but just be careful to make the training phase relatively short. So either limiting the number of epochs or using some kind of early stopping mechanism or using explicit regularization. So these two are good choices, also commonly used, but what needs to be clear, they easily overfit, so be careful and stop it on time. Otherwise, try Adagrad.
Okay.
Yeah.
Thank you very much for your answer, Stefan. And we will move now with a paper by Hao. There are plenty of questions for you, Hao. So the first question is by Dan Bernstein. He's asking the following. Normally, separate networks connections are handled in separate threads or processes. Have you measured the synchronization overhead, context, switches, cache misses, etc., in collecting scalar multiplication inputs from multiple threads and redistributing the outputs to those threads?
I'm not sure whether I understand your question. So we assume that TLS server is under high load and batches 4 scalar multiplications. And then we perform these 4 scalar multiplications in parallel using FX2. Yeah, that's it.
Yeah, I guess the question is about the cost of context cache misses, for instance, and switches. What if you have measured this overhead?
Not yet, because we haven't integrated our algorithm into the TLS protocol, so we haven't have this result. Yeah.
Okay, thank you, Hal, for your answer. And we have 3 more questions for you. So one more question from René Struck. He is asking you, did you also try to implement variable point scalar multiplication with twisted Edwards models, or is Montgomery ladder always better?
Unfortunately, we haven't tried with other algorithms or curves, but what you mentioned is worth it to have a try in the future. Yeah, thank you.
Okay. Second question by Dan Bernstein here is asking you, the paper Batch Binary Edwards proposed throughput optimized ECC software, but so far I haven't seen anyone tackling the software hassle of synchronizing crypto across threads, even if there is a performance gain. So do you have any comment about this paper, Batch Binary Edwards? And its implementation? I guess this is his comment.
No, thanks.
Okay. Okay. So this will be another way to go, I guess, with Batch Binary Edwards. And a second question by René Struck. Did you also try and implement P256 instead of only 259-19 curves? And if so, do you have throughput metrics? TLS 1.3 uses P256 as mandatory to implement. If not, any speculation?
As I answered before, we haven't tried our software with other options of algorithms or curves, and we haven't integrated our software to the TLS 1.3. So we haven't known the metrics or the result of other metrics. Yeah.
But he's asking, do you have any speculation, any estimate? How could behave P256, for instance? How?
You mean the speculation for the P256?
If you can more or less estimate if your technique is going to work equally well for P256.
I guess I just estimate normally it will have the same.
The same, right?
Yeah, the similar improvement compared in the case of
independently of the particular curve, or do you think that is important, one curve over the other, if they have the same size in bits for the final field?
So I assume that basically the improvement of the throughput that just similar as the case of the P256 compared to its latency optimized implementation. Yeah.
Right. Because we have yet another question just in the same topic. He said the question is Polish Sarkar suggested a slightly larger prime, which is p equal to 2 to the 66 minus 3. This is more than 4 words, 64-bit words. Maybe that would be different, don't you think? How?
So basically, I think we can still use 29-bit limp. Yeah.
Okay, thank you very much. You get lots of questions. So yeah. So I don't see more questions right now in Zulip. Anyone wants to ask any other question? I don't see it right now. So I have some questions for yeah, go ahead. Go ahead. Okay, I have one question then for Kalikinkar. One question for you, Kalikinkar. What is the cost of the masking protection that you are using, comparing with unprotected implementation of this authenticated encryption scheme?
Oh, the cost is basically I mean, so in our scheme, what we are doing, so we are replacing the AND gadget, the AND gates by AND gadget, TSNI secure AND gadget. The complexity of TSNI, for example, we need n into n-1 over 2, that many random bits. And also we need to have, once we expand the AND gadget, then it becomes order of n square XOR and order of n square AND gate. So the area is exploding accordingly. So basically the overhead we can think of is order of n square.
So for the specific instance of wedge that you attacked, what would be the amount of area that I need to pay for your protection? Like 4 times or
yes.
How many?
So for example, the unprotected implementation, the wedge has base area is 2900, which is less than 3000. But the protected implementation, the first order is 11.12. I think it's close to 11 point, let's say 11.5 if we did it. So now the overhead is about close to 5 times.
Okay, thank you, Kalikinkar. And I have a question for
close to 4 times. Close to 4 times.
Okay.
Yeah, for the first order.
Thank you very much. And I have a question for Aaron. Aaron, do you think that you can apply your techniques against Kalikinkar protection, masking protection, for authenticated encryption in wedge?
I'm fairly certain that our techniques can work against masked implementations, because the SAC2020 challenge was a masked implementation, and we were quite successful at breaking the software challenges there. Of course, we knew how the implementation works in that case. Yeah, I think these techniques, they can certainly be applied to masked implementations. In the case of the SAC2020 challenge, we used also some additional ideas that are not in this paper. But in principle, that architecture will scale well, and our neural network architecture will scale well, and it will work well also with some masked implementations.
Well, that's so interesting. So that begs the question, Aaron. What could be an efficient countermeasure against your attack? So you like masking is just falling apart with your technique.
No. I mean, masking is not just falling apart. I mean, in the case of the SAC2020 challenge,
okay.
we did find sorry.
No
we
problem.
did find a efficient way to see the masked chairs basically in the end. But this is of course specific to this this particular case. I mean, it's not.
Okay.
We won't be able to magically break any kind of protected implementation, because some implementations could of course be secure. But what our neural network does fairly well is it seems to exploit certain the features that were important for these challenges seem to be exploited fairly well by our neural network architecture. Yeah.
Okay. So just to finish this question, Aaron. So in your opinion, what would be, generally speaking, the best countermeasure against this kind of attacks that you are presenting? It depends on the scheme, or what's your view on that?
I think it would depend on the scheme. Yes, I think it's difficult to say in general.
It's just a broad question, right? Okay. Okay. Thank you very much, Aaron. And okay, so let me see if we have more questions in Philip. Yeah, we have one more question. No, it's just how answering. Okay. Yeah, I have one more question for yeah. So for Stefan, you mentioned briefly hyperparameters for your approach. Could you please explain a little bit more about how many of them are and how do you tune them up for the?
So basically, the number of hyperparameters depends on the type of the neural network architecture. So, for instance, multi-layer perceptrons, well, it has many, but common and most important ones would be, of course, number of layers, number of nodes in a layer, activation functions, and for instance, optimizers. For CNNs, there is much more because, first of all, there are different types of layers. So the number of convolution layers, pooling layers, fully connected layers. For fully connected layers, you would again have whether what's the number of neurons, what's the activation function. For convolution layer, you would have the number of filters, the size of the filter, the step. Then for pooling, you would have commonly either average or max pooling, again, activation functions. Then you would also maybe have dropout, you would have patch normalization, and so on, so on. So the number of hyperparameters is quite huge, especially for bigger architectures and larger data sets. It's not only about the number of hyperparameters, it's just that every test takes relatively a lot of time, let's say even only 1 hour. But if you need to do thousands of those or millions of those, of course you cannot do it. So people commonly do it in either with a random search, and actually we recently did experiments, and for commonly used data sets in side channel that are publicly available, even randomly selected hyperparameters do work well. If you have some knowledge on reasonable ranges, so you don't allow anything into the universe, but you say, well, common number of layers and this and that. Better option is to use grid search. Even better option would be, for instance, using something that has memory, so that you don't every time guess randomly, but have some drive into your process. So something like Bayesian optimization.
That's interesting, because that's what's going to be my next question to you. What is the real time of the attack? You said that 1 hour per trace, you mentioned?
Well, for the attack, the time is extremely short, because the attack should use as little as possible number of traces, and it's only the inference process. So it's commonly even seconds or minutes. The long time is the training. So you need to have big data set where you train, and you need to try many different architectures, so many different hyperparameter options to find very good performing architecture. And of course, the bigger the architecture you have, it's more complex, so it has more capacity, so it can model more difficult, more complex function. But of course, the bigger the neural network, then you also have more hyperparameters to tune, because in every layer there is something to tune. So I can tell you the longest hyperparameter tunings we did, it was on a cluster that lasted a couple of weeks.
Couple of
Weeks.
weeks.
So it's not crazy long time, but since we used decent number of latest GPUs, it's decent amount of time.
I see.
Yeah.
I see. Thank you very much.
Yeah.
Okay. For Kalikinkar, I have one more question here. You mentioned the number of shares. Do you think that you used in your approach, is that number optimal?
So actually, there are different security models, right? So here we consider TSNI. So for TSNI case, it's optimal.
Okay.
So yeah. So and if we, let's say, for example, we go for the threshold or other implementations, then it will be different. For threshold implementation, the minimum, like for first order protection, the minimum is 3. And if we go for the second order, then it's different. It's you know, there are some trade-offs. Minimum is 6. So it's like that. For TSNI case, it's minimum.
Okay.
So that is why we chose TSNI. But one of the drawback for TSNI is it doesn't prevent against glitches. But I mean, it works for I mean, other than like side channel, and also works for the software. So there are some for the microcontroller environment, instead of the when you are computing the S box, we compute the randomized lookup table that has the TSNI secure randomized lookup table computation, and with that we can secure for the microcontroller platform.
I see. Thank you very much. I have one more question for Hao. Talking about a higher order elliptic curves, like 384, let's say, do you think that your technique, how would you adapt your technique for that, for those elliptic curves that use more limbs?
The elliptic curve, sorry, could you please repeat the question?
For higher security levels in the elliptic curve?
Yeah.
For instance, if you're thinking an elliptic curve that requires, I don't know, 384 bits,
yeah,
how your technique could be applied?
So basically, with more limbs, it is generally to use Kurzhubel multiplication. So
yeah, but in
yeah.
terms of these having 4 at the same time would be problematic because you have more words.
Yes, but I think the performance will be still very good compared to the latency optimized implementation. So yeah, even though there are more limbs, because for instance they are shared the same instructions, so I suppose the performance is still better than the latency optimized implementation of the other algorithms.
Yeah. Okay, fair enough. So I don't see any more questions. Anyone wants to pose yet another question for any of the speakers?
I would have a question for Stjepan. Namely, if the double descent phenomenon, if it has been investigated on any synthetic data sets, or if it, and also if the double descent phenomenon would also appear if you look at the performance on the training data set, and on the performance in the performance on the training data set, if you don't average over all training steps, but if you evaluated the performance on the training data set at the same points where you evaluate the where you look at your validation performance, so that you run, if you ran performance evaluation on the training data set with a fixed set of weights.
For the question, let me first answer the first one. That was simple. The second one, I'm not really sure I got it fully, but I will try. So we did try also with, let's say, more synthetic data sets, but we did not really see deep double descent there. We think it's simply because with synthetic data sets, unless you add very large levels of noise, the data sets are simply too easy to break, and everything works so nicely that you don't really see the effect of deep double descent. For deep double descent, we really need to also to have a need to train it for longer number of epochs. So you also don't see it if you train it for a very short number of epochs. And commonly in side channel analysis, in many papers, you see people say, well, 30 epochs, 50 epochs, that's very short trainings to see deep double descent. And deep double descent also has, let's say, 3 flavors. So it's not only on the epochs, it's also on the size of the model, and it's also on the size of the profiling set. So researchers showed that you can have deep double descent if you train longer. You can have deep double descent if you use larger profiling set. You can have deep double descent if you have larger neural networks. You can have deep double descent. For now, we managed to see deep double descent only with respect to the number of epochs. So your question regarding the profiling phase, there we did not, if I understood well what you're asking, we did not notice deep double descent there, unfortunately, because that would be also very interesting, I think.
Okay, so the time is up right now. Thank you very much for attending this session. It was a very interesting discussion phase. And we are done with session 5 of SAC 2020. I don't know if the chairs want to add some more words.
Thank you, everyone, and thank you, Francisco. I think we're done for the day, and we will reconvene tomorrow with Ben's invited talks. So go to the website to identify exactly on what time it's going to be on your time zone, especially as now daylight saving times are slowly getting out of the window for various places. So see you all tomorrow.
See you.
Bye-bye.
Bye. Bye.
Bye.